Hello students, good afternoon. We have been revising the module 2 now. Even though it is here called as module 3, in our sequence we discussed source coding after the introductory chapter. So this is basically a method to encode the given symbols in the character set or in the source alphabet. Let me revise this formulae. We have two things here now. One is called HN cap and one is called L. HN cap is utilized when the block size is given, and L is utilized when the block size is not specified. Okay. So in the Shannon encoding in the beginning, we use this HN cap because their block sizes are specified in those exercises. Later on, we moved on to Shannon Fano, and for Huffman coding, there we use this term called L, even though both are same. In the sense, HN cap is the average number of bits per symbol in the encoded sequence for the block size N, whereas L is the average code word length per symbol when block size is not specified. When you look at these two formulae, you will feel as if HN cap is 1 over n summation of I equals 1 to q of NIPI, whereas L is equal to summation of I is equal to 1 to q of NIPI. So you will think that HN cap is having a denominator n. But the point here is that the block size n is specified, and naturally the results are slightly different that way. But essentially both are one and the same. Later on we had a derivation called Gn is less than or equal to Hn cap and it is less than Gn plus 1 over n, which indicated that when G is the encoded sequence with the block size n, now when we calculate the average number of bits per symbol in the encoded sequence, now this Hn cap is in between Gn and Gn plus 1 over n. And we had already seen this as a derivation earlier. Now what does this mean? It means that the average number of bits per symbol in the encoded sequence will be actually greater than or equal to the total information content in that sequence itself. And it will be less than the information content in that sequence plus 1 over n. So what is the meaning of this ultimately? What is the meaning of this particular formula? The meaning is that to have an average information content as per the given sequence, we will have to have at least these many average number of bits per symbol. We cannot compromise on the number of bits that are going to be transmitted that way. Otherwise, the information content will itself have a degraded quality when it is received at the receiver. That is the idea of this particular formula. When the block size is specified, the efficiency is given by E equals H by Hn cap. And when the block size is not specified, the efficiency is given by eta equals H by L. Now, we have been discussing the variable length code and the fixed length code, and I was telling you the example of ASCII code and extended BCD code, EBCDIC, in extended BCD. So, in the case of ASCII and extended BCD, advantage is data rate remain constant throughout because the number of bits for a given block size are constant. And the bit errors can be easily corrected. Why? Because as the number of bits for a given sequence are constant, we can actually, at the receiver, we can actually have them as partitions. All the received bits can be stored as partitions as per their sizes and each partition can be corrected as such. So bit errors can be easily corrected. Now the limitation is that all symbols become equiprobable because for every given symbol, the number of bits in the encoded data is same. That way, let us say from A till Z in the English alphabet, if at all we use the ASCII code for A till Z, then all these characters in the English language will have equal number of bits, which simply means what? Which simply means till A till Z all are equally probable that way, because we are not bringing out the probabilities dependency on the information. As we already know, information is inversely proportional to probability. The highly probable information is containing less amount, whereas less probable information or event is containing more information. But when we have fixed length coding, we are not taking care of such properties of the information at all. In that way, all symbols are equally probable, and in that case, data rate cannot be reduced because the number of bits in the sent stream is going to be constant. Whereas with the variable length coding, such as Morse coding and Shannon coding, here bits per symbol are reduced, as bits per symbol is based on the probability of the symbol. And another advantage, bits per second are also reduced. Here first thing is bits per symbol are reduced. I have purposely written as B/S to differentiate from BPS. B/S means the number of bits utilized for each symbol, they are going to be reduced because they are dependent on the probability or inversely proportional to the probability. Now bits per second or the data rate that is going out of the transmitter, that also is going to be reduced, as this bits per second is based on the block size. And we have already seen the relationship of entropy along with its block size. So in that way, if there are more number of bits in a given block, then the number of bits to be transmitted per block will be reduced. That is where I had shown you the expression earlier. What was that expression? That G1, G2 in the first module. Yes, this one. G1 is greater than G2, greater than G3, that way it goes on. It is greater than H, where H is the entropy of the source, where this G1, G2, G3 are the entropy of the sequences. That means G3 is having a less number of bits when compared to G2. G1 is second order, G2 is third order, it goes that way. Which simply means that when we combine symbols together, then there is going to be a statistical dependency between the symbols, and the statistical dependency is going to help us in reducing the number of bits when the sequence is having a larger number of bits or when the block size is larger. So that is the advantage here again. Yes, I was here. So the advantage here is bits per symbol is also going to be reduced because it is based on the probability of the symbol. Bits per second are also going to be reduced as BPS is based on the block size. So this bits per second is nothing but that capital R which we have been using. And bits per symbol is nothing but that small rs which we have been using. Now, the limitation of the variable length coding is that bit error are difficult to correct because they will have variable length. As they have variable length, later on you have to recall what all measures we had taken in the module 4 and module 5 to correct the bit errors. We used to have syndrome calculations, and using the parity check matrix, we used to correct the errors at the receiver. And we used to have cyclic codes in module 5, we used to have linear block codes in module 4. So those are all difficult processes which have to be utilized at the receiver. Whereas in case of an ASCII code or in case of a fixed length code, it is easy to correct the error because we know the number of bits which are present in for each symbol, and we can easily detect and correct the error. But in the variable length coding, it is difficult to correct. And then the second limitation is data rate remains fluctuating in the case of variable length coding. For example, let us say high probable symbols are going together, then high probable symbols will have less number of bits. In such a case, the total stream will have less number of bits. Let us say later on the low probable symbols are going together, then the low probable symbols will have larger number of bits. Suddenly the data rate will increase. This way data rate remains fluctuating in the case of variable length coding. But its advantages outweigh its limitations. Again, it depends on the applications. We can use ASCII code if it is only between, communication is only between the keyboard and the central processing unit, right? In the case of a desktop computer, keyboard is connected to your CPU unit, and in the keyboard also there will be a microcontroller or microprocessor, and even in the main unit also you will have a microcontroller and microprocessor. So from the keyboard, if the information is being sent to the CPU unit, it can be a fixed length coding there. Okay, that is because it is only a short term communication. Whereas if you have to use this fixed length coding for our voice communication, for mobile communication, then it will be very difficult for us. Reason is, unnecessarily we are increasing the number of bits. In the case of mobile communication or wireless communication, as the channels are completely shared, unlike in the case of a desktop computer. In the case of a desktop computer, between the keyboard and the CPU unit, there is a dedicated wired channel. But in the case of wireless communication, there are no dedicated channels. It is a shared channel. The shared channel has to be utilized by so many people. There we have to conserve the bandwidth for each user. So in such applications, we cannot go for fixed length coding. Unnecessarily it will increase the data rate. Data rate is related to the channel width and the bandwidth also. So in such real-time applications of voice communication or wireless communication, we go for variable length coding only. And later on we had discussed the types of codes. We used to call it as a block code when all symbols are mapped. All the symbols that are available at the source are mapped with their respective coding. Then that is called block coding. Now, a block code is called as a non-singular code when it is having distinct code words. And a block code that is non-singular is also called as uniquely decodable code if it is with respect to the sequence when it is uniquely decodable. And the block code which is non-singular, which is uniquely decodable, is also called as instantaneous code. It is with respect to the end of the code, in the sense at the receiver. At the receiver, it must be able to detect each and every code's ending, then that is called as instantaneous code. And finally, optimal code is the one which is going to have the minimum average code length. And in our earlier theory classes, we had seen an example for all these types of codes. And we are interested only in instantaneous and optimal codes at the receiver because we are using the variable length coding. For helping us in such encoding, we had a expression with us called Craft inequality. You can see that on the screen now. Here this is defined as k is equal to summation of I equals 1 to q 2 power minus li. This was derived earlier in the theory classes. Here q is the number of code words and li is the number of bits in a code. Now this equality has to be satisfied for an instantaneous code. That is how we used to use this Craft inequality. The instantaneous nature of the code can be verified with the help of the code tree as well by the observation of the absence of prefix property. For any given encoding scheme, you can write the code tree and you can visually inspect the code tree to find out the instantaneous nature. That is one way. Another way is the code tree can be converted into a graph, and to a graph one program can be written either using C language or any other such computer programming language, and through that program again the instantaneous nature of the code can be verified through the code tree. Those are other methods of verifying, and it can be verified mathematically by using Kraft inequality also. So I had mentioned one more thing there when we discussed Kraft inequality, that any code which satisfies Kraft inequality can be considered as instantaneous code, but it does not mean that every code that satisfies Kraft inequality is instantaneous. We had mentioned this and we had seen the example also. That means all the codes that satisfy Kraft inequality need not be instantaneous, whereas Kraft inequality is one of the necessary and sufficient conditions to check the instantaneous nature of the code quickly. That was the idea there. Now this is the revision of module 2 as such from our curriculum. Next, let me move on to module 3, even though it is here called as module 2. Let me move on to module 3 now. This is channel classification and capacity. Now at the transmitter we have capital R is equal to small rs into h, where that small rs is the bits per symbol and h is the average information content at the source, average entropy. And at the receiver, dt, or we should say the data transmitted, is equal to small rs into I of a semicolon b. This I of a semicolon b is called as the mutual information now. You should visualize those two circles which we have been discussing earlier, and if the transmitter and the receiver circles overlap completely, then we say it is a 100% error-free transmission, 100% error-free reception as well. But it is not the case always. That is when we represent it using two circles which are slightly overlapping. That slight overlap between the two circles, wherever there is that overlap in between them, that is called mutual information. That is represented here as I of a semicolon b. So at the receiver, it is basically whatever is the mutual information received from the transmitter, that itself is meaningful. Even if there are other bits that are received by the receiver, they are all not part of the information that was transmitted from the source. All those bits are part of noise only. So that is how at the receiver dt is equal to rs into I of a semicolon b. Whereas at the channel, what is it? At the channel it is c is equal to rs into I of a semicolon b maximum. This is called as channel capacity. The channel capacity is defined in this manner, where the mutual information's maximum value, that is corresponding to h at the transmitter, right? Rs remains the same everywhere, you can see that. Ideally, this h has to be here also in the second equation, that h has to be here also in the third equation, ideally. But practically, channels have their own limitations. Channels cannot have infinite data handling abilities also. So whatever is the maximum content of the mutual information, that indicates the channel capacity, and whatever is the actual mutual information for that particular time duration, that indicates the data transmission rate. Now based on these observations, Claude Shannon and along with these associates, they made some theorems, source coding theorems and channel coding theorems. Of course, the source coding theorem, I did not put it in the revision for the source encoders module, because that is quite simple there. It is already discussed earlier. Now channel coding theorem states that for a discrete memoryless channel that is noisy, discrete means what? Data goes one after the other. Memoryless means what? the channel does not have its previous memory, which means the statistical independence is shown there in the channel. Statistical dependency will be there at the source, but in the channel, there should not be statistical dependency. Channel should not be storing anything that way. So, a discrete memoryless channel which is noisy. Ideally, all channels are noisy. No, practically, not ideally. Practically, all channels are noisy. So, for a discrete memoryless channel that is noisy, the maximum rate of transmission is equal to the critical rate of channel capacity. The maximum rate of transmission is equal to the critical rate of channel capacity. Now, we can have this R also, we can have this dt also. We can have this R, which can be a maximum rate of transmission. But can it go through the channel? That is the question. If it can go through the channel, then the data rate and the channel capacity can be same. So, the maximum rate of transmission is equal to the critical rate of channel capacity. Stated otherwise, as long as R is less than or equal to C, an error correcting code always exists that will reduce the probability of error below any predetermined level. What does this mean? Let us say we have this C which is computed for a given channel. Now we cannot use an R which is greater than C. I had given enough live examples earlier also. Let me give you an example now also. The highway must be having that much of capacity only when those many vehicles come there. Let us say, for example, an 8-lane highway can carry only 8 vehicles at a time, right? 4 vehicles at the left side, 4 vehicles at the right side. That way, if it is an 8-lane highway, it can carry only 8 vehicles at a time. Now, let us say, due to some reason, maybe more than 8 vehicles come at a time on the road. Now, the highway cannot handle that much of traffic. Maybe due to some sudden calamity or maybe due to some important person's death, many people travel suddenly everywhere. Now, when people travel from everywhere, when people try to travel or when they try to come to a particular town or city, now, only for that day the highway cannot be expanded, right? So, that way the highway has a capacity of carrying 8 vehicles at a time. But there should not be more than 8 vehicles at a time which highway cannot handle. In the same way, channel is characterized by its channel capacity. It may be an optical fiber, it may be a coaxial cable, it may be a normal 2-pair wire, 2-pair cable also. Each channel will have its own defined capacity. Now the data rate should not exceed more than the channel capacity. Naturally, when more data rate is pumped into the channel, then the channel cannot withstand that much of data rate. Channel itself will introduce lot of distortions or noises during the transmission. So here the channel coding theorem says, as long as R is less than or equal to C. Now errors will occur not because of the channel. If R is less than or equal to C, error will not occur because of the channel. Errors will occur because of the internal and external noises. Channel itself will not cause distortion to the transmitted signal as such. But channel also will have its own noise as such. That is why I mentioned about internal and external noises. Now, if that is the case, then the theorem says that we can correct this error. As long as R is less than or equal to C, we can correct this error. For example, in an 8-lane highway, let us say an accident happens somewhere. If an accident happens, only 8 vehicles are coming at a time, and because of that accident, there can be a traffic jam there. Now, a police person can come there and he can direct the other vehicles slightly slowly. But it is possible that correction is happening there, and the police person can also urgently call for some other traffic clearing mechanism, such as if the a vehicle which has met with an accident, it can be moved to the service road urgently. So he can call for a crane, or he can call for some other vehicle which can pull this vehicle out of the highway. Until then, there can be slow rate of traffic there. Now that is an error correction capability which policeman is doing. This is possible as long as the capacity of the highway does not exceed. Then even if there are errors there in the channel, it can be corrected. But the problem is, if there are more number of vehicles coming on the highway, and then if an accident happens, even a policeman cannot clear it so early. A whole team of police people have to come there, and many people have to put a lot of effort for clearing the jam now. Now, in such a case, even error detecting and correcting will be more difficult, much more difficult, sometimes impossible. Sometimes, here also in Bengaluru, I have seen, if there is a particular traffic jam in a particular place, and there are more and more number of people are coming, and if there is only one particular police constable there, and if he is unable to clear the jam, he will try for 5 to 10 minutes to clear the jam. But let us say from all 8 directions vehicles are coming, and around the circle there will be a circle there, or there will be a street light post there. Around that, from everywhere, all vehicles are jammed. Now one police constable cannot clear that. And I have seen personally that sometimes this police constable simply go away from that place just for the people themselves to clear their own issues, because it is the people who caused that issue. Otherwise, a big team of police people should come, and from all the 8 directions, they will have to stop all the people from entering into the junction, and that is how they have to clear it. Now you can visualize the same situation here also for the channel coding theorem. In the sense, as long as the channel capacity is not exceeded by the incoming data rate, then it is possible to correct the error. Otherwise, it may become impossible to correct the error if R exceeds C. So here Shannon says, as long as R is less than or equal to C, an error correcting code always exists. We have seen by means of the parity check matrix, by using the number of check bits, n comma k code can be output, and using those n minus k check bits, we are able to detect the error, we are able to correct the error. That is what Shannon says here. An error correcting code always exists that will reduce the probability of error below any predetermined level, which means as long as R is less than or equal to C, then we can detect the error, we can correct the error, even if there is a probability of error which will be much lesser now. I had also told you about what is meant by BER, bit error rate. If bit error rate is 10 power minus 3, then it means that 1 bit error for every 1000 bits. That is what it indicates. So in that way, bit error rate, if it is still lesser, let us say 10 power minus 4, 1 bit error in 10,000 bits now, bit error rate can be reduced further. That is what is the reduction of the probability of error. Now the channel efficiency is given by what? The channel efficiency is given by eta channel is equal to dt by c. We already have this dt. dt is equal to rs into I of a semicolon b, the mutual information, and c is equal to rs into I of a semicolon b maximum. So eta channel efficiency is nothing but dt by c is mutual information divided by the maximum mutual information. How to find the maximum mutual information? We already have that expression, lg of m to the base 2, right? Log of m to the base 2, or lg of m, that we already know. So redundancy is 1 minus channel efficiency. So if 90% is the efficiency of the channel, redundancy is now 10%, or 1 minus 0.9 is 0.1, that is 10%. Using the entropy related expressions, the expression for channel capacity can be obtained now as C is equal to Rs into h of b maximum minus h of b slash a bits per second, or C is equal to Rs into Lg of m minus h of b slash a. H of b maximum is what? Lg of m. Just now I mentioned it. So channel capacity is nothing but symbol rate into Lg of m minus h of b slash a, which is called as equivocation. You will have to remember those two circles again now. The overlapping area is the mutual information, whereas we have the other non-overlapping area at the left side and the right side, that is called as equivocation, which is the information that is not actually received at the receiver. So for equivocation, we had a derivation and an expression. I am just showing you an expression here. H of y slash x, h of y in condition to that at x is equal to summation of I equals 1 to m, summation of j equals 1 to m, p of xi comma yj. What is this p of xi comma yj? That is called joint probability. You will have to remember the joint probability matrix now. This p of xi comma yj is the joint probability, and Lg of 1 over p of yj slash xi. What is this yj slash xi? It is the conditional probability, which means when xi was transmitted, the probability of receiving yj, that is the conditional probability. Always in the joint probability, we used to have the conditional probability also. We had a matrix called JPM, joint probability matrix, using which we could find out the value of equivocation also. Now, why are we finding out this equivocation? We want to find out the amount of information which is not received at the destination, right? What is the h of b slash a? A is transmitted and b is received in condition to whatever a has transmitted. So that is what is indicating the channel capacity, right? So if at all we have to find out channel capacity as such, we have to find out equivocation also, because it is the channel at which errors occur, right? Maybe due to internal noise, maybe due to external noise. Now in between you and me, there are so many network entities. There are routers, there are switches, there are switching protocols, there are 7 layers working between you and me. I had told you one acronym all people seem to need: data processing. Application layer, presentation layer, session layer, and transport layer, and network layer, and data link layer, and then physical layer. In between you and me, there are 7 layers working, which means in between you and me, there are so many communication equipment. Some are working at level 2, some are working at level 2 and 3, and some are working at level 4 and 5, 6 and 7 also. That way, when there are so many network entities between you and me, there are chances that errors are prone to occur anywhere and everywhere. Now, we should have an advanced information about the channel capacity in such communication systems. Otherwise, how do we define the data rate now? Based on the channel capacity only, we should have data rate now, right? Why this channel coding theorem was discussed? This channel coding theorem was discussed because knowing the channel capacity only, we have to send the data now. Knowing the capacity of the highway only, traffic should be sent now. For example, for an 8-lane highway, 16 vehicles cannot enter at a time. Even 9 vehicles cannot enter at a time. Only 8 vehicles can enter at a time. So that way, precaution has to be taken at the entry level itself, so that while they are traveling on the highway, there will be a smooth journey. Otherwise, journey may not start at all. That's what happens sometimes in Bengaluru also. From the international airport, all the way, all the vehicles come till Hebbal flyover. Till Hebbal flyover, all the vehicles come in a high speed because it is an elevated highway and it is a 8-lane, 10-lane highway. But what happens at Hebbal, in the peak hours when so many vehicles come to Hebbal, what happens at Hebbal? At Hebbal, in that flyover, there is a narrow junction where suddenly the highway converges into only 4-lane. Instead of 8-lane, now it is only 4-lane. Now, that is where at the Hebbal flyover, there is a heavy congestion on a daily basis. Of course, now during the pandemic period, there is no such traffic jam happening. Otherwise, on a daily basis, this is the scene at Hebbal flyover. Why? Problem is, from Hebbal flyover all the way, again from Hebbal flyover later on, after Hebbal is crossed, again we have a beautiful highway there. All the way till Chalukya Hotel, right? All the way till Chalukya Hotel, right from Hebbal, we still have a 6-lane highway, so to say. But why there is a jam at Hebbal flyover and why there is a jam near Kaveri Theatre? Problems are, there are those narrow lanes there. And that Guttalli underpass and overpass, what happens there? There what happens is, suddenly the highway converges into a overpass bridge there. And in the bridge, at a time, only 2 vehicles can pass in one direction, 2 or 3 vehicles. If there are buses, only 2 buses can pass at a time. That is the problem there. Which means what? At least Nyquist understood what is going to happen in the communication channels. But these people, when they planned these roads, they did not understand what is going to happen there. That is what is exactly happening now. Even though the other parts of the roads are quite wider, at some junctions there are narrow paths, due to which even now there are traffic issues and jams. So, in the communication, such jams should not occur here. In the communication, what does it mean? Jam means noises. So, noises should not occur that way. Communication should become uninterrupted, which means initially we should define the channel capacity. Later on, we should decide how much data to send through the channel. That is where this equivocation expression is useful. Let us say we choose an optical fiber for communication, then we should first understand the channel capacity. After understanding the channel capacity, how do we understand the channel capacity? By means of trial running. We can find out the equivocation here by means of trial communication. See, we have Lg of m, we have h of b slash a. Find out the equivocation by means of a trial run. That is h of y as y slash x. I have already told. This can also be expressed as h of y slash x is equal to summation of I equal to m of p of xi into summation of j equals 1 to m of p of yj slash xi Lg of 1 over p of yj slash xi. We had defined the joint probability in terms of the source symbol probability and the conditional probability, right? Now, using that, we can have an expression for equivocation. And equivocation is found out by knowing the probability of transmission, the conditional probability. Now, using that, we can find out equivocation. Using equivocation, we can find out channel capacity. Now, once we obtain the channel capacity, we should take care that the data rate should never increase beyond C. R should never be greater than C. If R is greater than C, then at the receiver also, it will not be able to detect and correct the errors as per the channel coding theorem. If the data rate increases the channel capacity, there will be more and more of distortions, more and more of serious issues at the receiver when it is receiving the transmitted data. and it may not be possible to correct the errors at all. Even if the receiver tries to correct the errors, those errors may not be fully correctable, in the sense you already know about the syndrome. If that syndrome vector is present in the matrix, only then correction is possible. If the syndrome vector is not present in the matrix, correction is not possible. Now, why such issues occur? The issues may occur because of this case also. In the sense, if R is greater than C, there can be errors which can be detected and they cannot be corrected. So, for any given communication channel, in advance the channel capacity should be known, and knowing the channel capacity only, the data rate must be fixed there. That is the idea of finding equivocation. So now, in case of symmetric channels, what do you mean by symmetric channels? The channels in which the probability is equal. All the rows contain the same elements but with different order. Symmetric channels means, let us say we discuss about the binary symmetric channel. Now P of 0/0 and P of 1/1, if they are equal, then that is called a symmetric channel. Now in case of symmetric channels, all the rows contain the same elements. Why they contain the same elements? Because the probabilities are equal, but they may be in different order. I mentioned you about a binary symmetric channel. There can be a ternary symmetric channel. There can be a quaternary symmetric channel. So there can be same elements in all the rows but with a different order. In such cases, summation of P of yj/xi, Lg of 1 over P of yj/xi for all the rows will be having the same value. And summation of P of xi is always 1, right? Because the source is going to transmit all the symbols and the total probability is going to be equivalent to 1. So summation of P of xi is equal to 1, and the upper term summation of P of yj/xi, Lg of 1 over P of yj/xi for all the rows will be having the same value when we sum it up, because the rows contain the same elements. Now h of y of x can be obtained from the conditional probabilities from any row. How to find out? The equivocation now. For the symmetric channels, we can find out h of y/x is equal to summation of P of yj/xi, Lg of 1 over yj/xi. You can compare this with the upper equation now. I am showing you both of them now. Okay, both are visible. Here you can see h of y/x is equal to summation of I equals 1 term of P of xi, summation of j equals 1 term of P of yj/xi, Lg of 1 over P of yj/xi. Now for symmetric channels, this term is going to be unity. Summation of I equals 1 term of P of xi is going to be unity. In that case, by knowing the conditional probability itself, we can find out the equivocation. It is not necessary that we should be knowing the source symbol probability. Look at this. That is what it means. The upper expression, when you compare it to the lower expression, what means is the summation of I equals 1 term of P of xi will not be unity otherwise, right? Now, because this P of yj/xi is also there as a conditional probability. Now, if we know the conditional probability at the receiver, that is enough. We don't have to know the source symbol probabilities. This is only in the case of symmetric channels. But in the case of asymmetric channels, what to do? In the asymmetric channels, we are supposed to know the source symbol probability. When it is unknown, what to do? When it is unknown, for that case also, Muruga gave a solution. We have seen the Muruga's method also there. Muruga gave a solution. Its proof is beyond the scope of our curriculum, but he gave an easy solution where, using that method, even for asymmetric channels also, we could find the equivocation. I hope you are able to relate all these things now. We have to find out equivocation in order to find out channel capacity. We have to find out channel capacity in order to decide upon the maximum data rate. And the maximum data rate is again given as symbol rate into entropy of the source. Now, the question is, let us say we have to fix R based on the value of C. C we have obtained by finding h of y slash x, and R we decide based on the value of C. Now, how to fix R? Only by fixing RS or the symbol rate. Ultimately, it comes down there only. Just visualize the example which I gave you about the highway and the number of vehicles entering. All of that boils down there only. The number of vehicles entering the highway has to be limited. That is the symbol rate there, isn't it? The number of symbols emitted per second from the source. Now, in order to avoid the traffic congestion, the number of vehicles entering into the road must be limited at the entry point itself. So, that is where again go back to basics. R is equal to Rs into H, where R should be less than or equal to C. C is now dependent on h of y slash x. So, ultimately we have to limit Rs only, small rs only we have to limit in order to have error detection and error correction. So, you can compare them now. H of y slash x can be obtained from the conditional probability from any row for that matter. That way our work is becoming easy only in the case of symmetric channels. Now, there is this derivation. Consider a channel matrix as follows. P of B slash A, all the conditional probabilities are given now. It may contain B1, B2, B3 at the